Ah, the good old Platonic solids. Earth, wind, fire, something, something, heart. Oh, wait, no, that was Captain Planet and the Planeteers. But we're going to be talking about some tetrahedra, and they seem to be quite snazzy. You all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. So, what are we talking about? All I know is the algorithm recommended a quite old live stream from my thing. Oh god, 2 years ago. I'm not even sure if I actually watched it with Professor Wolfram. But there's one thing I've learned: the algorithm can show you what you seek, whether you know you're seeking it or not. But basically, that was the video the other day that I clipped about him talking about closed forms and everything. And that got me to thinking there. Oh, hey Rick, hey Fractal, good to see you. Well, we'll get to that. We'll get to that. There's plenty more to investigate. It's just when you have new tools, especially to explore the computational universe, it's quite interesting. It's something where a noob like me can actually try to appear as kind of smart and stuff. I'm just saying, that's what some folks say. I would tend to disagree with it. But what the heck is a Platonic solid? Just real quick, in geometry, a Platonic solid is a convex regular polyhedron in three-dimensional Euclidean space. Being a regular polyhedron means that the faces are congruent, identical in shape and size. Regular polygons, all angles congruent and all edges congruent, and the same number of faces meet at each vertex. There are only 5 such polyhedra. 5, they say. And we get our tetrahedron, our cube, our octahedron, our dodecahedron, and our icosahedron. Basically, a lot of the primary dice one uses in Dungeons and Dragons. You might add in some d10s, but we kind of made those so we could do 10-sided and percentiles and stuff like that right there. Yes, welcome, awesome one. I'm unsure of the current squirrel population, but at least around here, I think they're starting to get quite bold. But all right, we got that, and yes, we're gonna do a little. The time when you go back and you're like, wait a second, trigonometry. Wait a second, do I even remember what the heck that was? Oh, you were doing this, you were doing that, you're doing that, and it's like, it seems to be boring as heck. That then also going through puberty at the time, probably. I'm just saying that there may have been some distractions. Yes. But I start going through this and I'm reading through. I'm like, Sokotoa. Oh my God, I remember Sokotoa and everything like that. It was a way to memorize things. And I just remember at the time, when am I ever going to use this? Apparently, what was it? How old was I? 16, 17? Yes. Teenage memes had no freaking idea. So what the heck is trigonometry? Trigonometry, oh look, triangle. And word a Cyrillic that I can't pronounce, metron, measure, is a branch of mathematics concerned with relationships between angles and ratios of lengths. The field emerged as the Hellenistic world during the 3rd century BC from the application of geometry to astronomical studies. The Greeks focused on the calculation of chords. Oh, well, mathematicians in India created the earliest known tablets of values for trigonometric ratios, also called trigonometric functions, such as sine. Throughout history, trigonometry has been applied in areas such as in geodesy, surveying, celestial mechanics, and navigation. Trigonometry is known for its many identities. These trigonometric identities are commonly used for writing trigonometric expressions with the aim to simplify an expression, to find a more useful form of expression, or to solve an equation. Yes. I see you there, Jez. I see you. Jez, it's far past your bedtime. What are you doing up, my friend? Then again, I ain't the boss of you or nobody. But yes, there's a lot of interesting stuff going on. But let's just jump into it. So all the things that got me into it was that video, and then I think Professor Wolfram said something like, "Oh, you find something like was the square root of 2 or 1 over square." He said something like that, and it got me to thinking. I'm like, wait a second. Isn't there something within like the quantum mechanics like system where it's like we apparently use the square root of 2 to figure out like the distributions for what's going on like within probability and stuff? I remember something like that, and I went up like Matt Stackett. I apologize. I done this like a day or so ago. And basically they're saying, oh, we're just measuring the probabilistic roots. And then I remembered, I'm like, oh, wait a second. That showed me, especially at the monastery, there's some very interesting things that might pop up. So, shall we? Oh, we shall. What is the magic angle? I done a video on this before. This is all starting to make a lot more sense now. Because apparently, what was it? I first heard from, I believe it was Brown University's physics department. They had achieved higher temperature superconductivity within multi-layer twisted graphene. I plotted the equation once. It needed a little tweaking. You can just copy and paste into Wolfram Alpha. But apparently it looked like it reminded the electrons there, they'll call them Cooper pairs and stuff. I'm like, it literally looked like they were swing dancers. It's like, swing your electron round and round, hand off your partner over there. I'm like, okay, that makes sense to me. I've done some like square dancing and stuff like that, where you're spinning around, you pass your off. I'm like, now again, I'm not saying that that's what's going on, but at least for a noob like me, it gives me a first level approximation. I mean, we're talking about like cats and superpositions and stuff like that, and we apparently take that seriously. I like cats, full disclosure. So, basically, the angle at which they need to do it was approximately the magic angle. It may have been a little bit less than the magic angle, to be fair to my recollection. What's the magic angle? It happens. You can just type it in here. Oh, and when you multiply it by 2, it's approximately, what is it? It's 2 tetrahedral angles, so it's about like 109.477, something like that, degrees, something like that. So when you plug it in, literally magic angle 2. It inputs the magic angle. That's a theta symbol. It's usually used for angle. So 2 magic angle. So you get the 2 secant minus 1 times the square root of 3. Oh, that's cool. So it gives us that number there. When we search for that number in Wolfram Alpha, there's some things that come up here. What's this? This is another theta, but it's a single one. Theta sub t? What the heck is that? How could we figure out what's going on? Well, oh look, theta sub t is the tetrahedral angle. What the heck is that? Oh, don't even let us know. When you actually go to Math World and stuff, it gives you another link. But we're just going over some very interesting things. Just because, and again, full disclosure, I'm totally biased on this. But if you happen to be part of a potential, like a think tank, where most of your model is based upon, like, I don't know, gluing together 2 idealized tetrahedron and folding them across to help create the complement of the hyperbolic figure 8 knot, triangles and tetrahedra get my attention. Okay, so what happens when you start playing around? Because I remember the square root of 2. I started looking through and I did like 1 over the square root of 2, and then only at like, I think like the 12th digit, because I was going through, I'm like, all right, you've got like, what is it, like 64 digits here? Let me take off like 30 of them. All right, go down to like 16, 18, like keep on going, delete a digit, and I'm like, wait a second. I think it was the cotangent. Where is it? Cosine. Where are we? Ah, yes, here we go. We're skipping ahead here. Okay. This is something that popped up. I'm like, huh, that's very interesting. We'll skip back. just for the sake of explanation's sake. Okay, we had our magic angle there. Okay. So, actually, well, let's reverse engineer this. It helps make it more interesting. Well, let's just take this number. We have that number there. Okay. So I believe here's what happened. Okay. So when you have the full number here, this is 1 over the square root of 2. Okay, so I did 1 over the square root of 2. Start seeing these things, and I'm like, oh, wait a second. E, Euler, or Euler's number, the base of natural logarithms, raised to the B4. I prefer B5 personally. B4 2 divided by 8. That basically goes into a lattice structure and everything like that, which is quite interesting, and you do see things like that when we're searching. Don't have a full interpretation of it yet, but it's interesting some of these things keep pulling up. But essentially, once I got down to, I think it was a 6 here. So like, yeah, like the 12th digit. Oh, no. Let's do it for impact's sake. All right. Oh, God. All right. We'll keep the 5 there. I know. It just seems completely pointless. But okay. We have our numbers here. We get that E, Madeline constant, 1 over the square root of 2, all these crazy things here. You're like, oh God, I can't parse that. And I deleted a digit. This is basically how I just kind of got down this Wolfram hole. The possible closed forms that popped up, I'm like, wait a second. The cotangent of theta t divided by 2? That seems like a very simple form. What is it? Go down. Theta t is the tetrahedral angle. Very interesting. And again, it doesn't give us that there. But basically, I believe it's half the magic angle there. So basically, when you're trying to figure out a tetrahedron, just based upon my little deep dive there, we're not going to go through all of this right now. But basically, if you're trying to figure out the angle between I believe the centroid there and one of the other vertices there, it ends up being like that, because it ends up being like 54 whatever degrees, and then it adds up to like 109. I'm probably butchering that. I apologize to all my friends with that geometry and trigonometry. I apologize. It's all right. Hey, welcome, Wow. Good to see you, my friend. But there is a lot of very interesting things. Oh yeah, and when you actually search out the tetrahedral angle, you find all this stuff within chemistry. Yeah, no fractal. No, you're basically nailing it there. I'm like, why? I'm just looking for this number for this angle. Why is it giving me all this chemistry stuff and everything? Apparently, that has something very important to do with the arrangements of different molecules and everything. So we'll just, it apparently seems important within chemistry. We'll leave it at that. Okay. So we saw that. I'm like, okay. So basically within, what is it, trigonometry, you have 6 primary functions, the trigonometric identities. So literally, sine, cosine, tangent, and the reciprocals are cosecant, secant, and cotangent. Okay. I remember putting those into like a TI-83. I think it was a plus at the time. I'm just like, what is the point of all this? Apparently, there's very interesting points. I think it was like 54, and so it adds up to be about 109.477, something like that. I believe so. There's some interesting numbers that come up as well. I'm like, so what happens if rather than doing so we take the tetrahedral angle, divide by 2. Literally, you're writing tetrahedral angle divided by 2. Throw in some brackets there. Let's just go through the different trig identities, shall we? We shall. So we get sine of the tetrahedral angle divided by 2. We're doing it in radians for more coherence. I would occasionally switch to degrees. I couldn't really parse it. Maybe it means something. To me, I can't really make much of it. So basically, it gives you this number here. The other interesting thing is the alternate forms for these. We got 1, 2, 3, 4, 5. Well, that's kind of cool. What happens when we click on that number right there? All right. When I click on that number right there, apparently that trigonometric identity is the square root of 2/3. It just keeps going. Like, there appears to be a computational equivalence there. That's kind of cool. Oh, and when you look at the fractions, they're pretty cool. This is literally, it's like 1 over 1 plus 1, 4 plus 1, 2 plus 1, 4 plus 1, and that seems to be a repeating pattern. So we move on to our friend, the cosine of the tetrahedral angle divided by 2. Okay, gives us this right here. What's the exact... Now, at first, I thought this was the Euler-Macaroni. Euler-Macaroni. I always want to say macaroni, because who doesn't like some mac and cheese? It's off. It's like 0.57. I think that's like a 2 or so. It's off at like the 3rd or 4th decimal place. The ultimate forms of this also happen to be 1, 2, 3, 4, 5. Oh, very interesting. Continued fraction is literally 1 and then 1, 2. Basically that same pattern, but with a whole bunch of 2s. 1, 2, 1, 2, 1, 2. Groovy. What happens when we search this in Wolfram Alpha? Oh, possible closed forms. It appears to have a computational equivalence to 1 over the square root of 3. Huh. And then you have the other identities. What is that? That's Trott's constant divided by 3. So I think that's normally like what is it? No, excuse me. That's Theodorus's constant. Oh, we're going real OG there. And then we got our cosine over the tetrahedral angle divided by 2. That's the ice. Oh, that's the 20 vertex entropy constant. So 2 of those divide by 9. That also seems to pop up a lot in a lot of these searches. So it's very interesting. I know Rick had something in there about, I think the D20. I believe that's 20 side. How many? Well, again, if we happen to have more or less a sum total of human knowledge at our being able to access it, I think we can better parse what's going on. I mean, we could just keep on arguing with each other. I mean, don't get me wrong. People need to call out other people for stuff and things. I just kind of got a little bored of it because it seemed like a lot of people just didn't really like each other and they were just looking for reasons. Just my opinion. But, all right, that's kind of cool. We continue onward. What happens when we take the tangent of the tetrahedral angle divided by 2? We got a decimal approximation right there. All right. We also have 1, 2, 3. We have 4 forms here, which is interesting. Okay. So repeated fraction is really 1 plus 1 over 2 plus 1 plus 2, 2, 2, 2, 2, 2. So we got all those 2's. We search it in here. Oh, we get that Euler thing again. Oh, let's make another appearance. What's this? There appears to be a computational equivalence with a square root of 2. Wait a second, wasn't Memes just yakking on about something with improbabilities with a square root of 2? I just found that a wee bit interesting. Well, that's all. And especially and again, I'm totally biased. I'm looking for those tetrahedra and anything associated with it. Why? Well, I'm not saying that reality itself may have some hinge points. It may have some hinge points. Conjecture on my part and potentially smarter people than me. We continue. We got the cosecant times the tetrahedral angle divided by 2. Okay. Our exact form. We got our decimal approximation there. We have our alternate form. There are 3 of these forms. That's pretty neat. And then this is the 1 over 4 plus 1 over 2. So 4, 2, 4, 2, 4. Wait a second. Seems to be a lot of 42s in there. Groovy. We go to our decimal number. Took a few off to look for some other things, but apparently that seems to be the square root of 3 over 2. Huh. Wait, so we had 2/3 and then 3/2. Huh. If only there was something we could try to figure out what's going on and what there may be an association there. But we continue. Go to the secant. That's a tetrahedral angle divided by 2. Cool. Throw that in there. And then you get the exact form. So it's like, oh look, oh yeah. But I've been skipping over these, but you're getting 1/3. I think there may have been a 2/3 in there. Just saying. We got our decimal approximation. This also has 3 identities. Pretty neat. And its continued fraction is 1 plus 1 plus 1 plus over 1 plus 2. So 1, 2, 1, 2, 1, 2, 1, 2. Looks pretty cool. Let's take a real quick look. What is does this have a computational equivalent? Oh look, it's the square root of 3. Huh. It's neat. Oh, and this is, oh god. Oh look, the 20 vertex constant, Trot's constant. What is that LSI? That is Lieb square ice constant. Okay, so that's another lattice construction over there. So basically, you get all those just different intersecting points of whatever you're going to make, kind of like a lattice. Like if you have like a garden or something like that, you'll have some of that little thin strapping fencing. That's basically a lattice. They literally call it a lattice. We also use that within like physics and condensed matter and all that fun jazz there. And I believe we have our last friend over here. Yes, the cotangent. And I believe this is how we got started. The tetrahedral angle divided by 2. Our identity right there. Yeah, as its 3 forms there. And as we started off, kind of just detailing the little journey over there. Yeah, basically it's has a computational equivalence to, it's like 1 over the square root of 2. That's pretty nifty. Oh yeah, its fraction is 0. It's 1 plus over 1, and then just all 2s all the way down. So yeah, I just thought that was pretty neat. I thought that was pretty neat, and just based upon this, some of the things I've learned from some really smart people, and occasionally Professor Wolfram would mention certain things and be like, he'd ask people questions and be like, well, what's this? It's like, oh, wait, well, there are people working on that. Somebody knows and everything. And every once in a while, like, he'll look into it, and occasionally, nobody's really looking into it. Or like somebody said they were, but they got distracted because they had other responsibilities. They had to do other things because, I mean, human beings are pretty complex, and hey, we're perfectly imperfect creatures. So we don't always get around to all the things that we mean to do. At least that's me. Totally projecting on the internet. But yeah, I just think these are very interesting, and they do happen to have a trigonometric correspondence to tetrahedron. I just think that's pretty neat. So probably nothing. But when I hear people talking about like the square root of 2 or 1 over the square root of 2, and it's like, this is very important. Might there be other interpretations? Maybe something we can learn. I'm pretty sure that there's a smart person out there, maybe watching right now, maybe temporally in the future, that can parse it better than this dude can. But that's all I got for right now. Peace out, everybody. Take care of yourselves. It's a wacky and wild world out there, but I think there's some good stuff right on the horizon. Savvy? Peace out.